Academia on the Line, a podcast where a couple of mathematicians take a look at what's going on in higher education. We're your hosts. I'm Joel Fish.
And I'm Karina Curto.
And what are we talking about today, Karina?
So we are talking about the Erdős unit distance problem.
That was like a pretty big result, right?
Yeah, that was a pretty big result. It was announced on May 20th by OpenAI that they had solved it. So there was this big open conjecture by Erdős about, asymptotically, as you have lots and lots of points in the plane, how many pairs will have exactly distance one between them. And he had a conjecture about this that
Yep.
has been open for 80 years, since 1946. 80 years. It's even older than us. Long time. And OpenAI found a counterexample, I guess, right? So they found that it's not true, or his conjecture is not true.
Yeah, I think it was a problem. He made some conjecture, and OpenAI disproved the conjecture, I think is roughly what it was.
Right.
But Erdős, he was kind of a crazy guy, right? I mean, I remember hearing about him as an undergraduate that he was a bit nomadic, and like there's an Erdős number. Mathematicians have an Erdős number the way there's like 6 degrees of separation from Kevin Bacon, I think. So kind of
Right.
crazy.
Based on collaboration distance, right? So
Right? Yeah.
do you know your Erdős number?
Oh no, I
There's like a website where you can put in your name and find out. I think.
I should probably check that out.
I don't remember. I don't know what mine is. I think it's like 3 or 4 or something. But
Wow, that's pretty good.
yeah, I collaborated with someone who collaborated with someone who collaborated with him. I don't know, something like that. But
Very cool.
it's yeah. But no, interesting fact. Like when I did Budapest semesters of mathematics back in
Yeah.
1999 as an undergrad, apparently I was living in Erdős's apartment. Like he had donated, not
That's
with him.
awesome.
He had donated his apartment to this program, to the
That's super
Budapest
cool.
semesters of mathematics. And so some students every year were assigned to live there. So
That's fantastic.
yeah.
Very
But
cool.
anyway, so he had a lot of conjectures, right? And one of the things that's kind
Yeah,
of
because he has like a big list of problems. I think I don't know how long the list is. I probably should have checked that out. Do you know how long it is?
I think it's probably hundreds of problems. I don't know.
Yeah, and he was offering cash prizes for them as well, right?
He used to offer cash prizes for them, exactly.
Huge
And
amounts of money, like $5, maybe
$20.
$2, $20.
Yeah, there were, I think that was like a level of difficulty of the problem. There were like $100 problems and like $5 problems. So I think, so anyway, but I think like there have been these announcements, right, about AI um,
Yeah.
systems, like ChatGPT Pro 5.5 or whatever, like solving some of these. Um, but this one is different.
Oh yeah, so this result is pretty big. I mean, there's been a lot of discussions on Twitter and I mean, general public, but then also I think math departments around the country and probably globe have been talking about this result.
Yeah, I think it's made a big splash. Definitely, I'm not on Twitter, but I'm on Facebook, and I have a lot of math friends who have also been talking about it. One of the cool things that happened with this announcement is that there was a companion paper with I think 9 authors, nine mathematicians who are, experts in the area, who just, basically explain the proof, but also give their thoughts and reflections on them. So it'd be great if we could get a couple of those to come and talk to us.
I guess we'll have to make some phone calls, see what sort of connections we have.
Okay, so we did make some phone calls and managed to get Daniel Litt and at the University of Toronto, and Melanie Wood at Harvard. They're both on that companion paper, and they have agreed to come and talk to us about it.
Fantastic. I'm really looking forward to this conversation.
I'm really looking forward to it too. Welcome to Academia on the Line. We have 2 great guests today to talk to us about AI solving the Erdős unit distance problem. And our first guest is Melanie Matchett Wood. Would you like to say a little bit about yourself?
Hello. Yeah, I'm Melanie. I am a professor at Harvard. I'm a number theorist. Is my mathematical interest, though I use math from a lot of different fields, from topology, probability, algebraic geometry. And I have been closely following the abilities of AI to help or not help, as the case may be, with research mathematics. And um, I'm really interested in thinking about the questions of how this is going to change our profession.
Very cool. And our second guest is Daniel Litt. Daniel, could you tell us a bit about yourself?
Sure, yeah. I'm a mathematician at the University of Toronto. I work mostly in algebraic geometry and number theory, and I'm also, interested in understanding how AI will affect the profession. And, yeah, I've been experimenting with it for a long time. Maybe since I don't know 2022 or something when GPT-3 first became available. But yeah, now I'm, starting to actually find it helpful for research as of maybe 6 months ago. So
Very
it's
good.
an interesting development.
And what was the first version that you tried to play with?
Yeah, so GPT-3, it was before it was publicly available, it was only available through a computer game called AI Dungeon, where you could subscribe for $20 a month, and then GPT-3 would kind of tell you a Dungeons and Dragons type story, which you could interact with in some way. And so I spent a lot of time in this video game trying to get GPT-3 to do math,
That's
which
fantastic.
yeah, this was
Within a
really it
Dungeons
was
and
real.
Dragons story.
Yeah, so my character would be a math professor, and they'd go into their office and try to do some math. And this GPT-3 was quite, especially the first version of it was quite bad at math, and so they must have had some prompt telling it not to do math because you would do things like, you know, I type into my calculator 8 plus 3, and then it would reply the calculator broke and did not output anything.
Wow,
That's
interesting.
fantastic. So I just could you get it to do anything that was sort of not Dungeons and Dragons based? Like if you said, I cast, I don't know, instructions on fixing my car engine. I mean, like, could you get it to do other
It
stuff?
would pretty much go with the flow, but I think there were certain things it would not want to do.
Okay.
So yeah, like yeah, it was probably pretty hard to get it to write, computer code or
Right.
something like that. But yeah, if you were telling a kind of innocuous story about a person going to work, it would
Mm.
happily, it would maybe try to inject a little bit of excitement into that, but it would happily continue and not introduce goblins or whatever.
This is
Fantastic.
this is 2022. This is before or after ChatGPT came out publicly?
Yeah, it was
Before,
right before it came out. Yeah.
before it came out.
But then, yeah, once it came out, so GPT-3 had a web interface, and there you could actually start getting it to do some kind of math. Like I think, I managed to get it to do things like prove Fermat's little theorem with, an unbelievable amount of hand-holding. So like, I was writing every fourth word or something in the proof.
Okay. Okay.
But yeah, it
It's
was it
like
was able to do a little bit of
like teaching intro to proofs.
work. Yeah, maybe even more challenging than
Yeah.
that.
So I'm curious. So roughly, if you guys remember, when was it? So there was a. So I only started looking to sort of see what it was capable of doing when you could ask it, okay, prove the square root of 2 is irrational, and it would do that, and then you would ask it, prove the square root of 4 is irrational, and it would give you the same proof. Like this was kind of my introduction,
Right.
but I don't remember what the timeline was. I think that's later than 2022, isn't it?
Yeah, yeah. So that was, I mean, so I think at that point, when it could start giving correct proofs of some statements and also, lots of,
Sure, sure.
it wasn't kind of thoughtful about its answer. That was probably, early 2024.
Hmm.
I don't remember exactly when GPT-4 came out, but it would, it could sometimes give correct proofs of
I
certain
think
statements.
definitely in spring 2023, I tried asking for a proof that there are finitely many
Hmm.
primes,
Hmm.
and it would basically give the proof of infinitely many primes, but changing changing the words. And so it'd be
But I
like,
think,
here's the
it
proof.
wasn't it wasn't thinking for itself. Like there
Yeah,
was no kind
yeah.
of like it wasn't robust to adversarial prompting in any way. So
Right, right,
as far
right.
as I
I'm
think
just saying, like at
wanted
that
to.
point, it was still kind of quite, quite bad in some sense. But yeah, a lot has happened in the last 2, 3 years, I guess.
Right. And now we have this great result out of OpenAI, which seems to have resolved Erdős's conjecture on the unit distance problem. And one of the cool things about this result is that it comes with a 9 author companion paper in which they discuss the key arguments from OpenAI's proof, or disproof, I guess, and also provide some further reflections on the problem in general and how AI might have come up with its results. Melanie and Daniel, you guys are two of the co-authors of that 9-author paper. And I was wondering if we could have you start just by letting us know how you got involved in that project. Like, how did you become collaborators? Who reached out? Things along those lines, if you could.
Daniel, I think you got involved first. Is that right?
Yeah.
So maybe you should start and then I'll say how it expanded.
Sure, yeah. So what happened was, so I guess they were testing various Erdős problems on their internal model, and it told them it had a solution to this unit distance problem, which is like a well-known problem in combinatorial geometry. And the solution used some kind of fancy number theory, which I guess no one at OpenAI was like had the expertise to check. So to the two mathematicians at OpenAI I'm friendly with, Mark Selke and Mehdi, reached out to me and Victor Wang, who's another mathematician, with this document asking like, oh, can you check this part of the argument?
So you just knew them? You were like you're friends with them, or how?
Yeah, I'm friendly with them, and also, I've discussed math things with OpenAI for, I've complained about their models in various ways, and so I know them through that. And yeah, so they we have some Slack channel we're all on, and they contacted me through that. Yeah, so they asked me to check it, and then once it seemed like it became clear it was correct. They also asked me if I wanted to contribute to this companion paper.
Okay.
And so then I think after Daniel and Victor had given a thumbs up, they reached out to a larger group of, around 10 mathematicians, again saying that they thought that their internal model had solved this problem, and they were hoping to have a companion paper. Their idea was to release the proof simultaneously with some commentary from human mathematicians. And I took that as a good sign that they were trying to really help put some context around this problem and not just try to be the next piece of the hype machine, but they wanted some serious people to say what was going on. And so then I think almost everyone, though not everyone that they reached out to, joined the companion paper. We all had email discussion back and forth with each other, and then discussion in Overleaf as we sort of wrote up our notes and redigested the OpenAI proof, and then that coalesced into this companion paper.
And so one of the questions we had was, okay, so this is not the first kind of Erdős problem that has been solved by AI. So there have been claims, in the last year or so of other Erdős problems. And of course, there are many, many Erdős problems. But this one seems to be one. It was open since 1946. I guess that's when it was posed.
Yeah.
So 80 years. So that's, but that's not always the sign of a big problem. It's like people should care about it, right? And have worked on it. Some problems haven't been solved just because no one serious has really bothered to give it a big effort. So what makes this one such a bigger splash?
So I think that it's precisely that some serious people have really worked on this. Often when people talk about, an open math problem was solved, it's been solved open since 1946, the news stories make it sound like hundreds of mathematicians have been working for 80 years on this problem. Here would be the real metric. What percentage of mathematician time has been spent on this problem since 1946? Okay, first of all, that you need a lot of zeros after the decimal place. It's very little. I mean,
even for big, yeah.
But even for the biggest problem, there are many more problems than there are mathematicians, first of all. So most problems, very few people have spent very little time on. But for this problem, there have been some serious mathematicians with a lot of expertise that have thought some non-trivial amount, some real time about this problem, and weren't able to solve it. So that is the first thing that made me notice it. Whereas I've seen, okay, this Erdős problem, that Erdős problem. But when I heard, particular people say, "Oh, I have worked on this problem," then I thought, okay, I'll pay attention to this.
Yeah.
I had never heard of the problem, for example.
I had actually heard about it because I have some, I'm friends with Net's cats, who I think is the distinct distances problem, which is a related one, right? Like
Right,
he
right.
and Larry Guth. And so, but also I have lots of combinatorics friends. So I had actually heard of it, certainly haven't worked on it. I didn't know anyone who had worked on it, but I had heard about it. So that caught my attention as well. But um,
And just to
yeah.
balance out maybe a little bit, right? Like, okay, so if we think about the percentage of all, working hours of mathematicians or whatever, it's very, very small. But on the other hand, if you were to think in terms of like, okay, how many mathematician hours have been spent on this problem? Or maybe, maybe weighted by one plus your H index, for instance, right? Like that, like probably that this problem is then becomes much more substantial, I think, right?
Yes, I mean, by that metric, I mean, you don't have to scale up out of percentages. Still, even in the percentage metric, it beats many other
Yeah.
problems,
Yeah.
whether you scale it by the H index or not. I mean, uh, it's yeah. So still, I think that this has been something that people have spent more time on and more serious time on than any other problem that I've heard, go by as having an AI solution.
Yeah, I mean, I would characterize this as like the first interesting result proved autonomously by an AI. But yeah, I mean, in terms of interest beyond like person hours spent on it or whatever, you can find textbooks saying, this is a central open problem in combinatorial geometry. Like there are fields like where everyone, in the field cares about it. And I think that's,
And it's kind of a pretty easy to state problem,
yeah,
right?
yeah,
So maybe that
probably.
gets us to our next question, which is, can you say, a little bit about the statement of the problem, or what was actually proven?
Well, the problem, it asks if you have n points in the plane, what is the maximal number of pairs of those points that could be at distance exactly one apart? So that's the unit distance. And for each n, there is some maximum, that's some function growing of n. And the question is about how fast that function is growing of n. And the part that is at issue here, this isn't like, oh, is it growing linearly or exponentially? It's actually a very small question about it's growing like into to some power, and what is that power? Is that power like a constant bigger than one, or is it one plus some function like one over n that uh, goes to one as n goes to infinity? So it's a sort of very fine detail in this exponent of the question.
Okay, so I just have a question. What happens, like if you put the points down in a grid, just like a square lattice, I have a point at every um, intersection, and then there's distance one between neighboring points, just a square grid. What is the exponent in that situation?
Oh, okay, great. Let's do that. Okay, so you have your endpoints. If you want to put them in a square grid, that's roughly root n by root n square grid. You've got that there. And then the points that are unit distance or distance one are just points that are in a neighboring row or a neighboring column. And almost every point in that grid has four neighbors. Now, the ones at the edges don't have quite as many, but there are only on the order of root n of those, so we don't have to worry about it. So that tells us that there's a constant times n number of pairs that are unit distance apart.
Okay, I see. So every like sort of interior point is going to have four neighbors, so it's going to go like four times n. But the point is the exponent is one in this case.
Yes, it's a constant times n to the one, and that's a lower bound. You can do at least that well. The question is, can you do better?
And what was Erdős's actual conjecture? What did he think the best bound was going to be?
Yes. So Erdős had the same idea to take a grid, except he took a grid that and scaled it down. So the idea is you just want to you want to take the grid and scale it to maximize the number of pairs which are unit distance apart. That's just the same as taking your grid of side length 1 and looking for pairs that are the same distance apart, right? Because then you can scale down by that length. And so if you have 2 points, the distance between them is like, whatever, it's the square root of the horizontal distance squared plus the vertical distance squared. So you want to know, can you write a number as a sum of two squares in a lot of different ways?
Uh-huh.
And so what
Okay.
he did is that's something number theorists understand very well. How many ways can you write a number as a sum of two squares? And so he kind of did that number theory, and he found that if you rescale a grid appropriately, you get something like n to the 1 plus some constant over log n.
I see. So we've gone from 1 to 1 plus a constant.
But it's 1 plus a constant over log n, not 1 plus a constant.
Which is gonna go to 0.
Yeah, that's the whole ball game is between 1 plus a constant and 1 plus a constant over log n.
I see.
Yeah,
An OpenAI solution, right, is that it's 1 plus a constant.
that's right.
That
Yeah.
doesn't decrease as n goes to infinity.
So he had this lower bound of 1 plus a constant over log n. His conjecture was that was best possible. The best upper bound was like n to the 4/3. So actually, I want to. You guys said OpenAI solved the unit distance problem. I think that's not true. So they
Okay.
disproved Erdős's conjecture about it. But
Okay.
okay, so now we know it's n to some constant, like maybe the best constant now is like 1.034 or something like that. And there's an upper bound of n to the 4/3, and we don't know where in between the truth lies.
I see. So it's
actually still
between n to the 1.034 or something like that and n to the 4/3. And we still
right.
don't know if we can't get up to 4/3 or close to it.
That's right.
Interesting. I see. So there's still a lot of math to do to
Yeah.
figure this out.
Yeah,
Yeah.
absolutely. So what just, Erdős had made this construction, as Daniel just said, and he thought, you probably can't do better than this. So his conjecture was essentially that you couldn't do better than his construction. And what's notable is that the community seemed to largely believe this conjecture. I mean, people believed you couldn't do better, and so they did a lot of work trying to prove that you couldn't do better. So when we were talking about this metric of person hours into it,
Mhm.
I think the vast majority of those person hours were spent trying to prove that Erdős's conjecture was correct, that you couldn't do better than this construction. In fact, probably very few person hours were put into trying to come up with a counterexample to show that you could do better than Erdős. Who would have the gall to think they could do better than Erdős? So,
So that's a big part of it, right? I mean, I've heard this suggestion, like as a mathematician, that you should, I don't know, spend the day trying to prove the conjecture and spend the evening trying to find a counterexample. But I think very few people do that, right? It's like you kind of either believe it or you don't, and you sort of only work on one side. Is that
Yeah, I mean,
maybe
also,
what happened?
yeah, you need an idea to disprove it. It's, you have to make. And one interesting thing, though, I think is like if you kind of imagine, I don't know how many applications the unit distance problem has, but if you imagine like probably upper bounds have more, I would think would be more applicable than constructions giving you a improved lower bound also. So if you're trying to understand combinatorial geometry more broadly, just understanding upper bounds better might also just be the natural thing to work on. Like it's still interesting to prove a better upper bound,
Mhm.
even if the Erdős's conjecture is false.
Uh-huh.
but we could probably all learn a lesson from this that we maybe should be spending a little more time in the evenings trying to disprove the thing that
Trying to
we prefer
disprove
proving
Erdős?
during the day. Well, or just, whatever we were working on.
Yeah.
Because even if you don't, sometimes that can give you some insight when you realize what's blocking you from disproving it. That can
Mhm.
inspire you. I think, yeah. Anyway, I think that we can all learn that we should take that kind of bravery um,
Mhm.
or
Or
devil's
ask AI
advocate
to do it.
position into our work a little bit.
Mhm. Yeah, or maybe we'll be asking AI to disprove what we're trying to prove.
Yeah,
Right.
I mean, I do that already. It actually is useful. Like sometimes it has disproved various things that ideas I had. It saves a lot of time.
So
Yeah.
I'm actually maybe a context question. So it seems like this problem comes more out of, I mean, it's considered more like a combinatorics or geometric combinatorial geometry. But even Daniel, you were sort of saying that this kind of question, like, okay, how many like positive integers can you write as a sum of squares is kind of a number theoretic question. And then we see this AI solution, which is very heavily algebraic number theory sort of approach. I guess I'm kind of curious, like, how many people who might consider themselves number theorists like spend some time working on the problem one way or the other.
Yeah, so I know of an example of someone who is so Jacob Zimmerman in his comments on the distance problem says he's a well-known number theorist, and he says he tried to disprove
Yeah,
it a little bit using number theory ideas. That's the example I know, but my sense is probably not a lot of number
I see.
theorists have spent serious time on this problem. I don't know for sure.
Can you guys say a little bit about the solution that now, like with the like what was the number theory idea and how did this improve Erdős's bound?
Sure. So, how do we understand as number theorists how many ways a number can be written as a sum of squares? And how do we as number theorists think about this grid?
Mhm.
Well, as a number theorist, you might think of the grid as the points in the complex plane that are of the form a plus bi, where a and b are integers. And that is a ring, the Gaussian integers, that is the first example of a kind of algebraic number theory ring. And in fact, if you have a way of writing your number as a squared plus b squared, what you actually have, if you're thinking about this world where you use I, is a factorization of your number as a plus bi times a minus bi.
I see.
And so for a number theorist, we reinterpret that, write it as a squared plus b squared, as factor it in this ring where you're allowed to use integers and I.
Uh-huh.
And so that's how number theorists know, for example, things about, writing, at least in modern language, how we would talk about how we know about how many ways you can write a number as a sum of squares. But for number theorists, Z adjoint I is only the first ring of algebraic integers. There are many more such rings where instead of I, you might use some other numbers like the cube root of 2, or a solution to an equation like x to the fifth minus 3x squared plus 2x plus 17.
Mhm.
That you might not even be able to write in terms of roots. But all of those algebraic numbers or algebraic integers, solutions to monic polynomials with integer coefficients, those all can be used to build other rings, and you could ask about factoring your integer over those rings. Maybe I'll let Daniel go on from there to say a little more.
Yeah, sure. So okay, so what the solution ended up doing, or what this construction ended up doing, is just taking the adjoint I and replacing it with some increasing sequence of bigger and bigger number rings inside of the complex numbers, where you could control the factorization of certain numbers well. There is actually a huge amount of freedom of how to do this. So OpenAI's solution took one route. The discussion in the companion paper took a slightly different one, although obviously inspired
And
by.
are we factoring, sorry, I'm just trying to follow that. Are we factoring one here? Like,
You can think of it as factoring one if you allow some denominators, or you can think of it as factoring a bigger number and then kind of
and
scaling
then you
down
can
to make
rescale it,
that.
but there's
Yeah,
some like concrete number,
yeah,
right?
that's right. Yeah.
And we're
Yes, you
thinking
want to
about
find one
factoring
number
them,
that has a lot of different
right?
factorizations.
And if it has a lot of different factorizations, that means there's a lot of pairs in the corresponding lattice that would have
That's right.
that distance. Yeah.
That's
Okay.
right.
Okay.
Yeah.
Okay.
And
Go
so
on.
yeah, so the construction was to take some kind of increasing tower of number rings in which some number had more and more factorizations. Um, the actual construction OpenAI's model used came from ideas of Golod and Shafraevich from the 60s. So they produced something called an infinite class field tower, and it turned out that had properties well adapted to this kind of construction. Specifically, they used a construction due to Hajir Marin Ramakrishna of infinite class field towers with some totally split primes. And an interesting thing is the chain of thought, which OpenAI released, specifically mentioned this work, but the write-up by the model did not. So it may be
Oh,
useful to mention that that
interesting.
this really relied on recent previous work. There's a huge amount of freedom on how to do this. Okay, so there are now counterexamples to the unit distance problem that don't rely on Golod-Shafraevich, that rely on much more elementary mathematics.
Now,
Um,
since this proof, since May
yeah,
20th.
since this proof, yeah. So
Okay.
there's just a huge amount of like once you have this idea of using
That was another question. It's like once you have this idea, right, you
yeah,
can improve it further probably, and there's
yeah.
other.
So it seems to me like maybe the easiest route is to use this Golod-Shafrovich, these infinite class field towers, and it seems to give the best lower bounds. But if all you want to do is disprove the Erdős unit distance problem, I think you have a huge, huge amount of freedom.
Oh, sorry, I want clarity on that just a little bit. So the idea that infinite class field tower seemed kind of central to the discussion, at least in the companion paper, but you're saying that that could be avoided now if you just wanted to disprove Erdős's conjecture. Is that right?
Yeah. So I think if all you want to do is disprove the unit distance conjecture, but not, produce the optimal
Right.
lower bound, it seems like that you can use much more elementary ideas.
Wow. Okay.
But yeah, even this Golod-Shafrovich stuff, like you shouldn't think of it as super fancy. Like it's,
Okay.
it's from the 60s. You can for an expert, it takes, 1 or 2 pages to.
But there's a huge world of counterexamples, basically.
Yeah,
That
that's right. I think that the key idea is to take a tower of number fields. I think
Oh,
that's
okay. So you still will definitely use a tower of number fields, though.
yeah, but you have a lot of freedom on how to set it up.
Even within the companion paper where we were talking about still using Golod-Shafrovich, we tried to gesture at the extent to which almost any choice you make along the lines will work. And now as Daniel said, okay, you don't even have to be constructing the number fields from a class field tower, but there's a huge amount of freedom. But what's interesting about these number fields, I do want to say, you're exactly right, Karina, how you described it, that we're looking, for a single integer or a number that has many factorizations. Those factorizations will correspond to many different pairs in a lattice. But for number theorists, that lattice is very high dimensional. So if you're taking algebraic integers coming as a solution to a polynomial of degree 100, they're in a 100-dimensional lattice. So when we say a tower of number fields, it is important we're talking about number fields of growing degree. And as that degree grows, the lattices are higher and higher dimensional. It turns out that you just project it down to 2 dimensions at the end. So you still get a solution. But when you take a 100-dimensional lattice and you project it down to 2 dimensions, what you get is no longer a lattice in 2 dimensions. It looks like a big mess because what was a nice structured lattice in 100 dimensions, when you project it down, doesn't look like a lattice anymore. So the points in the plane no longer look like they came from any kind of lattice, but secretly they're in this 2-dimensional shadow of 100-dimensional, 200-dimensional, million-dimensional lattice that got projected down at the end of the solution.
Yeah.
I see. Okay, thank you so much for clarifying that, because that is actually, I was trying to imagine these things in 2D still, and it's like you really have to go to high dimension and growing dimension, right? But then the projection, I guess, is chosen in such a way that you're going to preserve all these distances or the ones of interest. Is that hard to figure out the projection, or is that kind of a straightforward
No,
step?
it is a straightforward thing. In number theorists, we embed these numbers in this high dimensional space. It's called the Minkowski embedding, and in these constructions, you can project onto any coordinate of the Minkowski embedding, essentially. So
I see.
again, here it's not hard to get that part to work out.
Uh-huh.
Yeah.
So so when you project into the complex plane, it should still have some symmetries or something. I would think, right? I mean, is it like invariant by left shift and right shift by 1 unit, for instance, or something like that? I mean, it still has some symmetry, or no?
Yeah, I mean the patterns look quite beautiful. Yeah, you should think you take a very structured lattice, you project it, you still see some kind of repeating patterns and so on.
Do you have pictures of those patterns? I didn't see any in the companion paper.
Yeah, so I think Alvaro Lozano Robledo generated some pictures of not of the specific construction from the unit distance problem, which you can't really picture because it's a tower. Like you don't see anything interesting in any given dimension. But I think maybe he took some number field of degree 4 and showed some pictures of all the unit distances you get from some rescaling.
Would you send us a link to that after? That'd be great.
I think it was also in this, maybe there was a Scientific American article on the unit distance problem where they used this picture.
Okay, cool.
Yeah, I mean, I think it's a little misleading, right? It doesn't actually show what's
Yeah, it's not the actual one, but still, it conveys this idea of the projected lattice, right? Which is an important step. Okay, I learned a lot there. That was great.
Okay, so when you look at what Erdős did, he basically only used the standard square grid, but then has to rescale it in order to get more and more factorizations. But to get this result, you have to use really different sets as you change n, right?
The shape of the lattice of these other algebraic number rings is different.
Hmm.
You could see that even in two dimensions. Like if instead of z adjoin I, you adjoined something like 1 plus the square root of minus 3 all over 2, you get the sort of triangular hexagonal lattice. So when you choose different algebraic numbers to determine the ring of algebraic numbers that you're working in, that changed the shape of the lattice. So the lattices are all very different shapes. But then once you're in that lattice of that funny shape in that high dimension, you're still again basically looking for a number that has many factorizations, and that equates then in this high dimensional lattice and then in the projected lattice to pairs that will have a fixed distance.
Right, but it doesn't seem like you say, okay, we need to find this one really good lattice to work with, this one really good set of algebraic numbers to work with. Like as you increase n, you have to be changing that, I think, right?
Absolutely. Yep. So there's no one in where this is the solution. This is the example. The contradiction is not from a single um, configuration, but the fact that there is a sequence of configurations
Yeah.
uh, that growing larger and larger that violate Erdős's conjecture.
Mm.
So that's what this tower of number fields, the tower is referring to, that you're taking bigger and bigger degree number fields, which means that the sort of original lattice is in higher and higher dimensions, and in each one you get some solution, and as you let those go to infinity, you get a sequence that would violate Erdős's conjecture.
So
And
that's really
oh, go on, sorry.
no, I was gonna say that's really different from the sort of the naive lattice in the plane, right? Where there you really are growing. It's kind of the same configuration, but you're just adding more and more points, and you're not really changing the structure. Here you're like every time you're starting over with like kind of a brand new lattice. That's the and in higher and higher dimension.
I think you actually are adding more and more. Like, you can set it up so you are adding more and more points to one configuration. But again, there's a lot of freedom. But yeah, it doesn't have the same regular structure as the grid.
Okay.
Yeah. In fact, I mean, it's sort of interesting. Like you can ask, which is when does it beat the grid? And I believe, if I remember correctly, you have to take just an unbelievably huge number of points before the construction from OpenAI solution starts beating the grid.
Really? I see. So the grid is still better up until some large
Yeah,
n.
quite large. Yeah.
Uh-huh.
When we talk about these asymptotics, we
Yeah.
completely hide anything like a constant out front. When we say, n to the
Uh-huh.
1.03, you don't know if that could be that multiplied by a gazillion,
Yeah.
I see, but then but if I only have like 100 points and I was like, let me arrange them, for my kid's birthday party so that there's the most unit distances, right? I'm still kind of good. I might be better off still with the regular lattice
Yeah. For small n, there's also
or
lots of kind of sporadic known
the
constructions
sporadic
that
ones. Yeah.
beat the grid. But yeah, I mean, I think if you want to like you will never visualize the smallest configuration OpenAI solution constructed that beats
Awesome.
Erdős's for the same number of points. Like it will just never happen.
Okay, that's so interesting. I think our next set of questions is about what AI actually did to solve it, like how much human prompting was there, and something you mentioned earlier, we wanted to ask more about the chain of thought reasoning, like what is that, and and how was it necessary for their solution, and how was that involved? You guys can talk about that.
Well,
I mean, I think the answer is they just gave it no human prompting. They just gave it the statement of the problem and it solved it. At least that's the
That's
information
what
we
they're
have from
saying.
OpenAI.
Uh-huh.
Yeah, I personally believe it. What is true is that they probably have put every Erdős problem and lots of other problems into their model, and you know, it solved this one, which is a big deal. But I mean, it's sort of a buckshot approach, right? Like that's some kind of human decision to try it on everything.
Uh-huh.
That's very different from how human mathematicians work. Like we, pick, 3 or 4 problems and try to think about them a lot, rather than trying every problem.
I see. So they might have been working on 100 problems that, or more
And we
simultaneously.
know, in fact, that they tried this particular problem 100 times at varying levels of computes because they produced a graph showing, how often their model found a solution as a function of, how much compute they threw at it.
Ah, interesting. And how much I see. And so the chain of thought must be related to the amount of compute, right? So
That's right.
how
Yeah. So the model kind of writes thoughts in a scratch pad. Like this is how since September 2024, when the first reasoning model O1 came out, this is how kind of models have started to get good at math. They have a little scratch pad. They produce a chain of thought, and they think for a pretty long time. So for this particular problem, OpenAI released a summarized chain of thought. They didn't release the raw scratch pad, but some kind of LLM summary, which is 125 pages long. Probably the actual chain of thought was much longer, but we don't know.
Mm. And the chain of thought, I mean, is this like, can you think about this as being broken down into discrete steps? Like it's like 10 steps or 100 steps? Like how long is the
It's kind
chain?
of like if you imagine writing down your stream of consciousness, thinking about a math problem, like it's like that. So it's all the ideas the model had, all the things it tried, and at some point it has the idea of like thinking about a tower of number fields, and from there it pretty much just works out the problem just like a expert human would.
Just like this is sort of a question more on the sort of the nitty-gritty of how the model is working because it's like there is this notion of taking the output and feeding it back in, right? And that I can think of as happening in a discrete set of steps. But what you're describing is more
Yeah, the
amorphous.
model it just is one continuous run. It keeps thinking and thinking and
One
thinking.
continuous run and is outputting stuff along
Yeah,
the
and
way,
then
but
it looks back at what it wrote, that kind of thing.
it looks back at what it wrote, right? Okay. And then I see.
Yeah, so it has some access to a workspace and various tools that it can use, like it can write Python code and that kind of thing. But in this case, it seems we don't know exactly how it was scaffolded, but what we know is it had access to the scratchpad and was just writing its chain of thought for, however many hundreds of pages.
And that's happening anytime you use one of these state-of-the-art models that says, it's for reasoning or math or,
Mhm.
and you get access, you can have access to some of that. Usually if you click the little thinking text, you can see, again, that will just be a sort of summary of some of it. But my understanding is that what's going on behind that is it's producing a longer version of text, uh, of,
Mhm.
of how it's thinking.
Yeah, if you use an open model, you can actually see the raw chain of thought. But yeah, for like OpenAI and Anthropic's models, they don't release that because they want to stop people from learning from it and copying their models.
Is that the primary reason or the primary way the AIs are getting better at reasoning? So, like, I think if you like initially when the AIs sort of came out and you could use them, people were talking about like stochastic parrot. It's like it's just doing kind of the next best word in the sequence based on maybe looking back a few words or something along those lines. And of course, it's gotten better since then. But then, is the big improvement on math like exactly this? Some sort of a something which says, okay, I think for a while, I do some stuff on a scratch pad. Maybe that leads me to write some code. Maybe that leads me to sort of search the web and then feed that back to myself, and then you iterate for some period of time. Like, is designing that what's allowed the reasoning to get that much better?
Yeah, so I'm already like right. So the first so-called reasoning model came out in September 2024. Before that, you could already get way better like performance on math just by saying like think step by step or something like that. And then what would happen is the output would, it would sort of start writing notes to itself as part of its output. And I think a lot of what reasoning models are is just sort of automating that process and training the models to think for longer and think better. I think yeah. So O1, which is this first publicly available reasoning model, although I think there were a lot of like all the other frontier labs had their own internal reasoning models by then, I believe. It was like a huge step forward in math. But I think since then there have been a number of other improvements which are not just related to reasoning. So they like just the fact that it has a scratch pad. Like I think there's a number of other things which I can speculate on, but we don't know exactly how the models are trained.
Sure. So, common parlance, I think, on social media is they one-shot this problem, right? So they gave it the prompt and said, "Here's a problem, go," and it output a result. Then they said, "Well, it looks good, but we can't verify it. We have to sort of send this out." And I'm kind of wondering, do you know before they sent out the output of OpenAI. Did they refine it themselves internally, filling in sort of details? Do we know this? Do we not know this? I'm kind of wondering if like you really saw the full raw output when you saw their proof, or you think it had some human intervention before you saw it.
So they definitely they told it write this up in a text file, and then so I saw a version of that text file that I then made some comments on, and Victor Wang made some comments on, and they revised it based on that. And it's possible there were one or two rounds where they asked it to expand on various things before that too. So yeah, I don't know that I've seen the original output, but we have seen what is apparently the original chain of thought, and it did contain more or less complete solution.
But in particular, the version that they made public is a version based on feedback from Daniel and Victor, and it has some substantial changes, right? Like it works with a 2-class field tower instead of a 3-class field tower, which makes the argument much simpler.
And there's some comments in the introduction which are basically verbatim from like my Slack conversation with Mitov and Mark and so on. Yeah, so it definitely it included some comments and even changed the structure of the argument based on Victor's comments.
Oh, and even change the structure to simplify it, or
I would say there's a lot of choices in how to set it up. It made it a slightly different choice.
Okay, so sort of first draft, all core ideas correct, and then after some humans sort of tinkered with it, said, okay, actually there's some refinements that can be made, and then that's essentially what was sort of released. And then with the companion paper, I think you guys explained kind of what the AI model did, and maybe you made some changes, so some simplifications on your own as well. Is that true?
Yes.
Okay.
Right.
So we just sort of restructured the argument to try to emphasize here were the two pieces that had some content to emphasize what the interesting ideas were, and then to also show, as Daniel has referred to several times, the range of choices that one could have made in the solution. And I mean, we didn't even get to the full range, but just you never know with a construction like this. Maybe it's like walking a tightrope where you have to balance all of these different features you need, and there's only one way to thread the needle and get exactly the choice of parameters that will work. But that's not at all true in this case. And so, we tried to give a sense of that in our write-up.
The other thing I noticed about the write-up, right? So it is broken up, it's nicely structured into lemmas and propositions and so on. Did the OpenAI output have structure like that?
Yeah, it tries to write like a conventional paper. I would say that what the models, at least right now, without some scaffolding or prompting, are not very good at is like emphasizing key ideas. Like they'll often, write everything kind of at the same level of detail, or spend a lot of time on like trivial standard stuff and very, very quickly go through the main idea or something like that. And that's one reason why there's a human write-up, is to sort of write it properly. So it's sort of funny. I mean, I think they're much worse at writing math than they are at doing math, which is
like many of us.
that is true. But I find it very hard to read model output like in mathematics. Like it's much harder to figure out what's going on than reading most human writing in my.
Related to that, how long was the initial paper that you actually saw? Because I imagine the longer the paper, like the worse it is in terms of really trying to figure out like what's going on.
So the initial draft I saw was like 10 pages.
10 pages.
Like
okay,
that.
It's still substantial, right?
Yeah, it wasn't too bad. And it was well, also like they kind of drew my attention to the part they weren't sure of, so it was like pretty easy for me to.
I should say, when I got the draft that I first saw, which is more or less the draft that was released, was, again, not very long. My first thought was, oh, no way. No way am I going to spend my time trying to read AI output, because, like Daniel, I've been trying the best models on things, and yeah, but in this case, it was a case where the key idea, even though the paper didn't do a great job highlighting it, it was not that hard to pull it out of the paper. And then you could just do the proof yourself once you knew the key idea. And I should say that's generally probably the most efficient way to deal with AI output. I was just at a
And human output. And
well, maybe human output too, but
And
Yeah, I was gonna
certainly
say.
AI output many times. Many
but
times
here's
it
that.
produces some long thing, and you
Yeah.
realize, wow, I could just reproduce this myself faster than I could read it. And so, really, you want it to be structured so you can figure out, well, is there like a one idea that I need in this to do it myself?
But okay, but precisely because of this, right? It seemed really important that there were sort of number theorists or experts in these ideas to be reading this. Like if you had sent the paper to me, right, I probably would not have been able to figure out the key idea, right? Despite the fact that this is all ostensibly there, and I am a mathematician and so on, right? So I think that's sort of a question. Like, would someone who's not an expert in the circle of ideas that are being used here have been able to pull out the proof or verify the
um,
proof, or did it?
the ideas are, not, if you were sufficiently motivated, you could learn what a class field tower is in a couple days and figure it out. I think it's not, yeah. I mean, it would be much more challenging, like like
Mhm.
there was some basic, my main contribution to checking with this was there was some lemma with that, in my view, was like totally standard. And they were like, is this true? And then I was like, yeah, that's true. I know how to prove it. Like I didn't read the proof of the lemma in the note. Yeah.
I see. Interesting.
Yeah. But yeah, I mean that probably you would have to read the proof or like open up Neukirch algebraic number theory and figure out the proof of
Uh-huh.
that or something.
So for a mathematician outside of the field, right, it would take longer, but you still think it would be doable. It wasn't like you needed um, that expertise as
And
your only chance of understanding it.
and in fact, like right, we are saying people check this proof and that is important. But if you think about like what did OpenAI do? Like they were throwing thousands and thousands of problems at the
Mhm.
AI and generating to each problem probably multiple solutions, and then they weren't reading those solutions, right? They didn't. There wasn't a human reading all of thousands and thousands of output. What they had was a grader, and the grader said this solution. I mean, a grader model, sorry, and the model said this solution is correct, and it was right about it.
I see. So they had a pre-filtering. So by the time they sent it to humans, they had already said, okay, this passed our grader
Yeah,
checks.
and what is true, I think, the models are still not super reliable, but they're getting much, much better at checking correctness of their output. And so, compared to a year and a half ago, like if the model, if you get some model output and then you feed it back into the model and ask, is this correct? And it says yes, like it's now, often kind of worth reading, at least in my opinion.
So this brings me to a question. So this is a quote of yours, Melanie, that I saw on social media. I don't know if you know this is circulating, but I sent it to Joel. I was like, we should ask her about this. And it said that it may be that AI models are better at convincing humans that they have a solid proof than they are of constructing a correct mathematical argument. And so I was curious if you could comment on that.
I think that the AI models are absolutely designed to do the quickest and easiest path to whatever you're asking them for. And unlike a human that might have a motivation of really wanting to be right and know the answer to some question, and I'm not saying that's everyone's motivation, but many of us as mathematicians, that's why we do this. Um, the AI does not have any interest in having an actual proof. It just is trying to convince you if that's what you're asking it for. Um,
Mhm.
I agree with Daniel that certainly over the past year, the models have gotten better um, at catching errors in text, whether produced by them or humans, and finding errors, which is great. I think that's really important. But I also think that they have gotten better at hiding errors, um, in that I still find plenty of errors, but they are very good at packaging content in a way that the error is subtle or hidden. So I think
Mm.
that's worrisome, um,
Yeah.
because of course humans can be tricked. Yeah.
Yeah.
So,
Yep.
and so one comment about this is so like Melanie said, they're trained to do this, and I think that's like literally true. Like one way they improve the model's capacity at mathematics is they have a
Hmm.
grader model and a solver model, and then the solver model produces a proof, and the grader says this is yet correct or not, and then if it's correct, they give the model some reward. Like that's and if the grader finds an error, they give the grader some reward, and they're trying to ratchet up both
Mm.
the grading capability and the solver capability. So that's like my understanding of how of at least one training paradigm. And so yeah, the model literally is being trained to fool a copy of itself. One way to fool, to pass a grader is to produce a correct solution. My experience is like capabilities are improving. So like if the model can produce a correct solution, like it probably will. And then if you ask it something too hard for it, it will often say like, oh, there's some theorem in the literature which is like subtly different from what's correct, which is very useful here, and it will find some way to prove the theorem. But that said, like as of a few months ago, the models sometimes say like, I don't know how to prove this, which is like a crazy, like it's a huge change, and like I don't know, in November of last year, they would like never say, I don't know how to prove this. And now, sometimes
I
if
see.
they can't prove something, they'll actually say, I don't know how to prove this. Like, here's what I tried.
So I've noticed when I have like so I use ChatGPT, and I'll have like these long conversations. I didn't realize that like it's not. I think this is kind of an interesting feature. It doesn't just send whatever your most recent prompt is. It sends the entire conversation, like all the way through. So if you're measuring by token use, that this is a quick way to burn a lot of tokens, I think. But um, what I've noticed in long conversations, especially if I'm talking about math or something technical, is sometimes it does make like a typo type mistake. And I'm kind of wondering, like, if it's doing that, okay, it's probably making sort of other things. If I call it out explicitly, like, oh, I was confused when you said the following, it'll say, oh, yeah, thank you for pointing that out. It was a mistake. But I do kind of wonder, like, if I'm not catching those mistakes and you're feeding it back into itself, like, does it just build on those mistakes? Like, what kind of happens? Because if so, the longer an argument gets, the much more likely it's going to break down and do something nonsensical, right?
I mean, I've found that sometimes it corrects mistakes in previous
Mm,
answers on its own. That said, like my experience is like the longer a conversation goes on, the dumber the
mm,
models get. Like, just because there's so much in context, like, and some of it is relevant, and they
mm,
get confused. Um,
And actually, beware, it doesn't necessarily pass back the entire conversation, especially if it's
mm,
doing reasoning. The context window can be much shorter than you think because it includes perhaps its like
mm,
private chain of thought. Because I've had a
Mhm.
math conversation where I defined some term, we've had several back and forths, and then in the conversation, it doesn't know the definition anymore because that's scrolled out
mm,
of the context window. So, uh, and I think that the length of that is a little bit invisible to us because it's not just what we see, but partially maybe some of
yeah.
the scratch pad that is filling up the window. So you don't know exactly how far back or which pieces of your prior context are being sent. So I do think short conversations is the way to go.
So that's interesting. But that seems like something they could make more transparent, right? Maybe there could be some sense where it tells you this is how far back it's going.
so if you use Codex, which is it's like OpenAI software that lets you use ChatGPT on your computer, and it can like use your computer for you, like write code and execute it on your computer. It will sometimes, as you have a longer conversation, you tell it to do something. It will sometimes say that it's compacting the context, which means that it's looking at all the things it's done, and it kind of produces a summary for itself, so it doesn't need to keep track of everything.
And you can see that. You can look at that.
Yeah, you can see that it has compacted the context. You can't see what summary it has written.
Let me see.
But yeah, and sometimes you'll notice it does that, and then like, oh no, like everything starts going wrong.
I don't know, Joel, do you want to transition to our sort of part three of the interview?
Sure, yeah. So this is a big result. It's an annals level result. I think that's kind of the general gist, I think, like the top journal in mathematics. And so if artificial intelligence can be proving things that get published in top journals, then there's sort of a question, do we still need professional mathematicians?
So we're asking this in a very sort of provocative way, by the way. But some people are saying this seriously,
Yeah.
Yeah, absolutely.
right?
So
So
first of all, with that question, you could mean we imagine that AI is going to get someplace in 5 years, and if it got there, what would we need? And then that really depends on what you're imagining. But right now, I agree that AI can be helpful. Sometimes it can be very helpful in writing code for me, but still, I find it even unable to do the very basic things that I would hope for it to do when I want help with my research. Like recently, I had an argument. I had already done it written out a detailed proof in an interesting case that should have included all the difficulties. I wrote a detailed plan for how to do the general case. And, it's far too specific. You could never give this to a student because it left no room for any difficult challenges. And I asked, the ChatGPT 5.5 Pro extended to fill out the details, and it just couldn't at all. So to me, yes, you see some little pieces that it's spectacularly good, but as far as just being a mathematician doing what we're doing right now, we are not seeing that it can do what we do most of the time in research. I mean, yes, there was this one thing when a 1 in a million, it really lucked out in this problem. But now, is it getting better? Absolutely. Might you imagine that it's someplace very different, in another year, in 5 years? But I just want to sort of, as a baseline, say that right now it still has a long way to go to even be a solid research assistant to a human mathematician.
Yeah, I mean, maybe let me just agree with that. Like, it's really very uneven. So, I have a bunch of different projects. Like, one of them is what I consider my main research program, and for that, like, frontier models are basically useless. And like, it's just because there's a lot of theory building, and there's sort of much more imprecise questions, and that they're just not good at that sort of thing. Like, they can often be helpful if you have like a well-stated lemma, or you're doing some literature search, and you want a proof of some very small thing, like that can be useful. But in projects which are at the stage where that's not yet what's happening, or where the hard part is finding the statement of a lemma, like that they're not so useful for that most of the time. On the other hand, because I experiment with the tools a lot, like now I also have some projects which I've like designed so that the tools can be useful, like because I'm experimenting with them. And it is possible to find, areas of algebraic geometry, for example, where the models are very, very useful. And that's quite different from how things were, 6 months ago, say. So the trajectory is really very rapid improvement. A year ago they just got a gold on the IMO. 2 years ago they couldn't do anything. So I do think like we should seriously think about like, if that trajectory continues, it's not guaranteed to happen, but it could. Like then what will the profession look like? And my expectation is that the models will, at least in some dimensions, keep getting better pretty fast. Maybe one way to put it is I think right now the model is like one really good mathematician, like meaning it has certain strengths, and if you ask it a problem which applies to those strengths, then you can hope for a really good answer. One really good mathematician that everyone can access definitely changes how the field will develop, but it's very different from replacing us, right? Like,
So I heard somebody say that, it's almost like this problem was kind of in the convex hull of existing knowledge, right? And it was a matter of putting things together. And so when you mentioned theory building as something it's not as good at, right? It feels like there's a difference between sort of solving a problem where the tools are all kind of there, right? And it's a matter of putting it together. And like certainly all IMO problems are of that style also, right? And then there's the idea of like a research program that's sort of building up a theory to sort of, solve some bigger questions. And maybe, do you see AI getting to that point where it could like come up with good definitions, come up with, good conjectures, or is it going to be a while before we get to that stage?
I think we should certainly prepare that may be a possibility.
I think it will be. I expect it to happen, and I think a while will be like a year or two. That's my.
A year or two, I see. That we'll have theory building.
Yeah, I mean it's just things are happening so fast. You can already definitely see signs of it. In the process of solving a problem, you always you play around with things, you make little conjectures, you read the chain of thought, and you can see they have sort of glimmers of these capabilities. Yeah, I think it'll happen. Yeah, there's one still kind of expects it to be uneven, and like doing mathematics is like a very high dimensional thing. Like so, as long as the model has some predilections that are different from ours, like I think we should expect that it will be doing things one way, and maybe we'll be doing things a different way. Maybe it will be doing its things very cheaply and very rapidly, and that might be able to substitute for other other capabilities it might lack. But yeah, we don't really know.
There's no reason to expect that the models are going to grow exactly among the dimensions of human mathematics. I mean, I think they are going to improve, but they might get better and better at doing certain things that could still be very helpful to mathematics, but might not be the things that we think of the best human mathematicians as doing. They don't have to line up with us exactly. When we use this story saying, oh, an IMO, and then, solving an open problem, we're imagining like a trajectory of a human mathematician, but they may just grow in other dimensions. I mean, as Daniel was already saying, he's now thinking about a problem that is kind of geared towards, oh, what would the models be good at? And we may see that happening with mathematics. Mathematics may shift a little bit if we get this remarkable new tool that's really good at some things, but not at others. And people think, oh, well, I want to work in this exciting place where we have this exciting tool. So I think that the models are absolutely going to get better, but it's not so clear in which of these multi-dimensions they're going to get better faster or sooner. But we should be prepared. I think we need to rethink a lot of things about how our profession is structured to make sure that we're prepared for these changes and whatever improvements come from the models.
Maybe let me just give an example to give a sense of my view of capabilities growth. So, historically, one thing that has been highly rewarded in mathematics is like solving an open problem. So, you write a paper saying I solved an open problem asked by such and such and such and such in a year. Obviously there are open problems and other and more serious open problems, and we try to make some distinction between that. But if you're solving a lot of open problems, that's like a sign, you're a productive mathematician, maybe historically. Right now, you can open up ChatGPT 5.5 Pro or Codex or whatever. You can say, go online, find 5 open problems in algebraic geometry, solve them, and write up text solutions. And if you do this, I've done this experiment in Codex on my computer. You can spin up subagents to do this in parallel. And I got 3 correct solutions to open problems, from recent archive papers. Like, were they interesting papers? No, like they're not things that I would spend my time publishing. But like if you wanted to produce, 5 papers a day that would have been publishable in respectable journals a year ago this way, you can do it. And there are people, if you watch the archive mailing list, there are definitely people doing this. And so like we have to change how we are, rewarding, like how we're hiring, how we're evaluating people. Like it's just there's now a glut of this kind of result that, historically would have been rewarded. And maybe I should say like you can produce maybe 5 correct papers like this a day if you wanted to. If you don't care about correctness, you can probably produce 100 papers like this a day, and maybe 80 of them would actually be correct, and none of them would be that interesting. But
And I feel like you're absolutely right, Daniel, that the profession and the incentives do reward this. But I feel like that was always a mistake. As you're saying, these things weren't that interesting. Really, we wanted to be rewarding people and incentivize people to do interesting mathematics. But then there's all these practicalities if you have to have hiring committees and you have to have deans who aren't mathematicians approve candidates and so many things that people have started to look at, publications and journals and all of these shorthands for what has this human, like what is interesting about what this person's mind has contributed to mathematics. And we take all kinds of shortcuts in measuring that. And I think now we're realizing that those shortcuts are really, really misleading indicators in the age of AI. In some sense, what we want is, humans who are creating, understanding, holding in their brain wonderful and interesting mathematics. That's what we always wanted, and that's still what we want. But now our proxies for measuring that may become much more fallible, even though they were always somewhat fallible, we should admit.
Yeah, I mean, I think this is, right now, whatever changes in how society is structured, like the new technologies like AI are putting some pressure on the profession. And like, as you would expect, the parts that are starting to crack are like where there were pre-existing flaws. So yeah, I think there's all sorts of like changes we're going to have to make, and they exactly reflect pre-existing issues with our institutions and the profession. So, like Melanie was saying, like the journal publication system, like how we're evaluating, like the various proxies we're using to evaluate people. Also, like, uh, how we evaluate students now is going to have to change, and I think that also reflects kind of flaws in how we've historically educated students. Yeah, it's a chance maybe to make the profession healthier in some ways.
So, in terms of shifting to get different metrics or assessments or whatnot, like I thought about this a little bit. Do you think it's things will become a bit more personal? Right, it's more like like on an easy scale, you could say, okay, instead of like for our undergraduates or something, or even graduate students, instead of a written exam, we want to do like an oral exam. But then if you're talking about someone who's going to graduate and get their PhD, for instance, in some sense, you want to make sure that they haven't just fed all these problems into AI and they're just sort of spitting them back. So I guess one thing you could do is try to have a conversation, and I can at least imagine maybe there's a pathway where you have something that's really more. Yeah, more personal interaction and discussion, and something a bit more, a bit deeper, I guess, than shallow H indices or something. I don't know. What do you think?
Absolutely. Of course, this is what the best version of our system was already doing when a PhD student graduates, and is applying for an academic job. Their advisor writes a letter of recommendation, which hopefully reflects that, over the time that they spent with this student over many years, the the mathematical insight that they saw from this student. I mean, so the best version of our system was already doing something like that, but we're going to need to lean into that a lot more. I think, yeah, I think that will be important in the future, and I think that all PhD advisors need to take this as a serious part of their job. It's no longer sufficient for your student to have produced something, produced a thesis, and you say, okay, they must have understood something. You, as an advisor, need to have talked to that student extensively and made sure that they really, really understood something, because the PhD needs to stand for understanding mathematics, not being able to just produce some content that may have come from an LLM.
And for what it's worth, I think the precise shape of how we evaluate students is going to have to depend on how capabilities grow. Like, if, for example, the models grow in a very uneven way, like probably we'll just start to value the stuff they're good at less. Right? Like, if I don't know, let's imagine. I think this is sort of unfair to some fields, but like imagine the models become really good at combinatorial geometry. Like, are we going to still be, as excited to hire someone who's working in that area? Like, I don't know.
But it's a weird contrast to what we said, I don't know, or you said a few minutes ago, where you say, oh, AI is really good in this area, so maybe more people are going to work in it. But at the same time, you might sort of say, yeah, but AI can do that stuff. We want stuff that AI can't. So it's a
Yeah,
weird balance.
I think it depends on whether those people are adding value, right? And I think there is a world where there's certain mathematical activities where people no longer add value. We don't know if that will happen. It's also possible that happens with like the production of all mathematical outputs. And then I think we really have to think, well, then what can the AI not replace? It's like human understanding or
Yeah.
something like that. And maybe that's where we end up valuing, but that's very hard to measure. Like, there's not really great proxies for that. And also, it really means, the math department becomes a lot more like a humanities department. Like, we're not measuring based on outputs as much. And so I think, we can decide if that's the profession as a whole has to decide, like, if that's the direction they want to go. But, I think it's really hard to make that decision without understanding the shape of future capabilities.
So I want to bring up sort of maybe an analogy. It's an imperfect analogy, right? But it's like if you think about applied mathematics and computers have transformed how that works, right? So it's like if you think about the emergence of computers being used to do simulations, to solve PDEs, all this kind of stuff, right? That's been going on for many decades now. It did not make applied mathematicians obsolete, right? It did not but it's no longer so impressive to be able to sort of maybe calculate a difficult integral or solve, I mean, there's a sense in which these are all now things that are just being used. There are new fields that have grown out of this. So I think like fields that are sort of scientific computing or numerical analysis Numerical analysis is a field, right, that sort of is about how to get the computer to make good solutions, right? Or to do calculations on a, good calculations that are reliable and so on. Do you see like, you know, pure math sort of, I don't know, developing a new field like that, right? Something analogous to numerical analysis, where it's like now it's about learning how to effectively use AI. Is that going to be like a new skill set, or I mean, I don't really know what I'm asking, right? But it's like I sort of see this analogy, and I'm not sure how this is different, or maybe kind of the same as what we've seen historically, just with computers in math.
I certainly am an optimist in that I imagine the future will be that LLMs provide tools that really supercharge mathematics and allow human mathematicians with the use of these tools to do math, far at a pace far beyond what we were able to do, certainly opening up new fields. And, it's hard to say if some of the fields of how to best use the LLMs might be more like fields of computer science or fields between computer science and mathematics. Who knows where exactly they will be? Certainly, I think
Mhm.
that will be an important area of study. But my um, my imagined future, I will say, still imagines there are humans doing mathematics with the use of these incredibly powerful tools, but how we do that and what parts we do may change dramatically. Um, it's if, for example, we haven't talked about formalization, but formalization is a process via which mathematical arguments can be rigorously checked by a computer. And if um, LLMs become significantly better at formalization, and we come to a world where a mathematician could, come up with a statement of the lemma and then get a certification that that's definitely correct or something, that just really changes what it looks like to do math. So yeah, I think that there is a lot of space for imagining a future of math where we have incredibly powerful tools and are able to do things and do mathematics in a way that are very different from what we do today.
Yeah, I mean, my view on this is like what you're observing in applied math is like there are certain things computers are very useful for and good at, and certain things they're not. So now your activities, focus on the things they're not good at, and you use them as a tool. And definitely, I think in the near term, that's what like LLM assisted mathematics looks like. Like there's certain things LLMs are very good at. For those things, we use them as a tool, and for things they're not good at, we use our brains. Or things where we're better, things that we're better at than the LLMs. I don't think it's guaranteed that in the medium term, those things continue to exist. Like I think it's possible that LLMs have all the capacities that human mathematicians do, and then it's not clear to me like what value we're adding by using them as a tool.
Mhm.
I'm not saying this is guaranteed to happen, but like it seems like a plausible outcome we should be prepared for.
And you really think it will be LLMs?
Or LLMs plus some architectural. Yeah, I mean, I think the main thing missing now from the LLMs is like that they have very weak understanding of new objects. And okay, Peter Schulze is like inventing a new kind of space every
Mhm.
year. And so if you want to use that to do mathematics, or like you develop some new theory and you want to use that to do mathematics, the LLMs are not so useful for that. You can like give them a paper and they can read it and like try to work with it, but they're much weaker at it than objects they know well. So I think that's like some architectural gap where like probably you need some improvement, or at least like new LLMs trained every year to get good at using the latest kind of space out of Bond.
Mhm.
But yeah, I mean, it's not so hard for me to imagine, sort of not like there's a lot of things people haven't tried yet. Like LMs are very, very new technology. There's huge, huge amounts of ideas for architectural improvements that just have not yet been tried at scale. So I
Mhm.
think we should expect them to get way, way better. Like there's a lot of room to grow, is all I'm saying, and it seems to me like that it's quite possible that we'll have like there's sort of obvious limits on what kind of numerical analysis a computer can do. Like in particular, it can't have an idea of like a new thing you might do with numerical analysis. Like LLMs clearly can do those sorts of things at some level already, and so yeah, it's not. I don't see what the blocker is that's going to prevent them from having all the capabilities we have eventually.
So, well, I might assign a lower probability to this possible outcome than Daniel. It sounds like he thinks that is a reasonable chance. I do think that it's possible enough that we need to think about it and to think about what we want in a future where it could be possible that LLMs can exceed humans by some definition in all of our mathematical abilities. And I would argue that I think preserving humanity's understanding of mathematics is incredibly essential in such a world. I mean, let's just point out that these machines are built upon mathematics. The idea that we would train a bunch of machines that are better than us and then risk the humans losing the understanding of the kind of theoretical ideas that are necessary to even build these machines sounds like a really scary dystopia. So I feel like even in a world which I don't think is guaranteed, but I think it has some positive probability of being the future, that a world where AI could exceed human mathematicians in all of our capabilities that we currently consider the capabilities of human mathematicians, we would still, as a society, want a structure that preserves humanity's understanding of mathematics, even if the new mathematics is being developed by the AI.
And one comment on this is like right now, academic mathematics serves two purposes. Like we produce good science and we produce human capital. And I think that second purpose, human capital, like historically, those two purposes have been really aligned. Like we produce human capital by training people to do good science. Like it's possible that a lot of good science will now be able to be produced automatically. Like we're starting to see some, high quality results produced automatically. But yeah, that goal of producing human capital will certainly, I think, is still going to be very important.
Yeah, I just wanted to say I 100% agree with you, Melanie. Although, in my kind of more pessimistic view of society, I think this actually is almost likely to happen. Not so much in mathematics, but more broadly, I think, as AI starts doing more and more stuff for us in society, I kind of worry that, and I'm kind of convinced that to some extent the more problems society sees, the more you throw at AI, and the more society doesn't understand like the solutions that AI is sort of coming up with, and you end up with a society where it doesn't really understand how it's got its like some of the core institutions or core functions of society, and then a problem arises that AI can't fix, and they don't know how to fix. Then they've lost a lot of the infrastructure for themselves, and then we have a big sort of AI collapse. So I don't know. I think something like that actually could happen. But math is not the focus there. It's the broader society, I think.
That's a good movie. We should make a movie about that.
Well, one way in which we play a really important role in this, we are talking mostly now about research mathematics, and when we were thinking about training research mathematicians. But as members of mathematics departments, we also teach a wide range of undergraduates, not just those who are going to become mathematicians, but people going into every field of science, basic introductory college level mathematics. And that I think is a place where we have an important role in this fight to not just worry about research mathematics, but to preserve that, as wide a possible slice of humanity continues to develop the kind of thinking skills, the rigorous thinking, the quantitative analysis skills that come from, introductory college mathematics. I think that it will be tempting to say, well, AI can do these things. Why should people need to learn them? Of course, the mathematicians have always had this fight. My calculator can multiply. Why do I have to learn how to multiply? And I think that we have a really important role if you're worried about this future to fight against it by being part of the conversation to make sure that, not just this ivory tower of research mathematicians continues to get trained, but that, a big portion of humanity understands uh, college level mathematics. An even bigger portion of humanity understands high school level mathematics, hopefully near universal. So I think that will be very important to the future.
So I really worry about this though, right? Because I think, going sort of further broadening from what we do, like to education, I mean, I do think that students with AI tools are now not doing their homework in the same way that they were before, right? I think that our mechanisms for transmitting this kind of knowledge to younger generations are breaking down because of these tools. And so I think on the one hand, that's very worrisome. On the other hand, I think there is a public conversation, not just about math, but including math, which is saying we don't need as many research mathematicians anymore. We don't need as many math professors anymore. Because part of what supports our jobs, right, is that we're teaching math to undergrads, right? And when the undergrad can just have a conversation with ChatGPT and, believe that they're learning everything that way, right? Do we really need to take so many math classes? Does the engineering student need to take so many math classes when they can just like ask AI and get, you know, further training or further answers? I think there is a real risk to the value of what the math community provides.
I mean,
Um,
my thinking here is right. Like, I taught a course out of Hartshorne's algebraic geometry book last semester, and Hartshorne's algebraic geometry book exists whether I teach the course or not, right? But people mostly are not, not learning from it themselves. Likewise, they can
Mhm.
ask ChatGPT a question and maybe feel like they're learning, but like, so what are we providing by lecturing or assigning homework or giving tests? Like it's mostly like an institution that gets people to do the work. And my sense is like governments and our other like funding institutions like kind of recognize the importance of that. Like the existence of ChatGPT can't really substitute for like institutional structures that like get people to actually do the work. I mean, there's definitely like we have to persuade them that that continues to be the case, but that seems like an easy sell to me actually. Um,
Really?
the question is, yeah, I think so. I mean,
Yeah, I mean, I agree with you. It's like everything is in books, right? So you're like, why should we have to teach algebraic geometry? People can just read Hartshorne.
right. But
That's
nonetheless,
funny because that is actually the book of the class that Melanie and I took together.
right. But what I mean is like we already have persuaded people of our value there. I mean, I think the question is like, will people continue to value mathematics at all? And that is maybe a little bit of a harder thing to sell if it can be completely if everything a mathematician can do can be completely automated. But on the other hand, I think if you in that world, like you should kind of expect everything a person can do, like and all intellectual activity can be completely automated. And so what are people going to do? Like assuming they don't want to just sit on their couch and watch TV all day, like what matters maybe is the relative usefulness of various activities. And I think mathematical thinking is always going to be useful. So I think there's a lot of ways we can still, there's a lot of very reasonable routes to persuade our institutions that like a big part of what we're doing is still valuable.
I feel like there's a lot of possibilities. I agree on that front, but I also feel like it's definitely an uphill battle, right? Like I think, especially if you look, there's a lot of colleges and universities that are closing. There's the demographic cliff. There's, you've got like a very anti-academy sort of executive branch for the federal government. You've got a lot of people losing confidence in higher education. A lot of people questioning sort of value. And when you look historically, I mean, you've got like what West Virginia University is the only R1 I think they had in the state, and like the state just said, yeah, no more graduate math program. You guys are done with that. We don't need that, right? And that was a year or two ago, I think, right? It seems. I don't know. I feel like it's a dark path moving forward for a while. I don't think it's going to terminate, but right. I think I don't know. It doesn't look so positive to me.
I mean, sorry, I agree with you about all of that, but I think that's sort of about trends that are kind of orthogonal to AI. So like maybe that will continue for a while, but presumably that, as you say, that doesn't.
I mean, maybe the trend is orthogonal to AI, but I do feel like AI is going to be used as an excuse, right? I mean, it's already being used to sort of cut funding in certain areas. Um, And, there's like right now, if you look at NSF or, there's a lot of funding for AI related stuff and then cuts
Yeah.
elsewhere, right? So I think this is like, whether it's really an AI effect or AI is a pretext, I do think that there is a danger right now in how the math community is valued. Um, so
Yeah, we should pull apart some of these threads. There is this demographic cliff. If there are fewer college-aged students, fewer high school students graduating in our country, some colleges are going to close, and that's difficult and um, unfortunate, but that's not part of some systematic problem.
Mhm.
And so we're seeing that, overlap. And, you were talking about, uh, I think confidence in higher education is definitely down. But if you look at how higher education rates among institutions, you say, well, what's your confidence in higher education? What's your confidence in the president, in Congress, in the Supreme Court, in your banks, so higher education is doing pretty well in relatively in terms of confidence, and a lot of people also have higher confidence in their local institutions than they do in those far off Ivy League places. And that's what matters the most to most people is the community colleges, their state schools. So I think that this situation is, I agree there are challenges, but I think it's not quite as bad, but we should take seriously how do we make the sell um, for the kinds of ways that we teach people to think. I agree that is an important task that we have ahead of us.
Do we have a venue for that? Is the AMS working on this? Like, I mean, it seems like you need to have kind of a unified message and a mechanism to deliver it to people who have the power to do something if they listen. I don't know. Is anything being done?
The AMS does lobby Congress, but I don't know, yeah, what their specific message
Right.
is.
yeah, I think right now the message is don't cut math
Yeah.
funding, just generally, right? Um, but I don't know if there's a specific AI related.
Yeah. And one kind of funny thing, by the way, you mentioned that all the money is going to AI now. If you think about what's going to be automated first, like the goal of the Frontier Labs is primarily to automate AI research.
Mm,
Mm.
Right. So it's a little bit funny that, yeah, as you say, the NSF is now funding a
yeah.
lot AI, quite a lot, but like that's, if they're
Hmm.
successful, that's the first thing that where funding
Hmm.
for humans will no longer be necessary.
Mm.
Yeah, it's interesting. I mean, NIH too. I keep getting these announcements about neuro AI because I'm in neuroscience, right? And so it's like everyone is like trying to jump on the AI bandwagon because that's where the money seems to be right now. But Um, yeah, it's funny. It's sort of backwards, right?
Yeah, it's
There's more money in the thing that's going to be automated first. I mean, I had one more question. Speaking of, money. So these models, the top models, right, that you guys are using, they're not cheap. I mean, I don't know if you have special access because of, being part of this companion paper or maybe some relationship with the AI company where they're giving you free access. But if we're talking about a world in which we imagine, the whole math community is like using these tools, right? And it's expected that you can use them. Who is paying for this? I mean, we just had a discussion here at Brown within the computational neuroscience, right? About how like we discovered a lot of our students are just paying their own subscriptions, and maybe we should be helping to fund that. But it's like there is an issue here. The tool is not free, um, and the level of the tool that you can afford changes how useful it is.
Look,
So,
right now, things may change, but right now, the sort of max subscription models cost $200 a month. So for an individual user, that's $2,400 a year. If you compare that to budgets of research, that's still really nothing. If you're paying a graduate student, and the stipend, might
mm,
be 40 to 50,000, maybe you're paying 50,000 again in tuition.
yeah, but if each of those grad students, will they all get their own subscriptions? Do you know what I'm saying? Like, is everyone?
I mean, if that becomes an essential tool, but
Mhm.
look at any scientist running a physical research lab. you have to pay for your tools. You have to pay for your, computing tools, your biologists, maybe you're paying for sequencing. I mean, eh, like
Mhm.
research does cost money. Right now, the the models are available at a rate that I think is well within the sort of scale of what we're already paying in research costs. For example, what we pay graduate students, it's much, much less than, it doesn't affect the first couple of digits of what it takes to support a graduate student in a year. So, um, and
Mhm.
but it may be that that's part of funding for math research that comes with this new expense. We're used to not having too many expenses. We said, oh, we just need a pencil and paper. But in any kind of physical research lab, yes, of course you have expenses to do science.
I mean, we do buy computers for grad
Right.
students, right? So
Yeah.
you think it's like a that.
So right now, as Melanie says, costs are pretty low, and like I don't know, you can ask how much does it cost to produce like a good result, like this unit distance problem, and like you can estimate that based on the length of the chain of thought. It costs probably not more than $1,000, probably much less. Um,
That's not counting all the failed
not kind
experiments,
of
right?
yeah,
All
just
the
for that one
right?
run, yeah.
Just for that one run, the one that worked.
But when I say not more than $1,000, that's like super conservative. Like I would guess under 100. You can look at first
Hmm.
proof, which is a really cool test of AI capability to prove lemmas that have appeared in the life of a working mathematician. There they don't use subscriptions; they pay API costs, and you
Hmm.
do see improved performance if you spend more on API costs. So to some extent, at least if you've scaffolded models appropriately. So, for example, one group was able to answer correctly a question that other groups were not able to, and they spent almost $1,000 answering it. So there's a question about if you get improved performance for increased cost, how much are you willing to spend? And in particular, like if you think maybe you can prove a result for $1 million, but not $100,000, then I think the world of math research looks very, very different, right? Like if there are results that cost, $100 million or, $10 million, like how are we getting that money? How are we apportioning it? Who has access to those kind of models that can run for that long? There are models like sorry, not AI models. There's like institutional models where this sort of thing is already reality. Like if you want to do astronomy, you need access to radio telescopes. Those are very expensive and have a very limited resource. And there's like committees that decide what part of the sky to point your radio telescope at. And like if it does turn out that we end up with models, and I think this is quite plausible, that we end up models where you get improved performance for increased cost, like maybe that's a big part of what our profession starts to do is like deciding on where to aim that radio telescope.
Maybe to change gears sort of slightly, I'm kind of curious. I know, Daniel, you've said like, oh, you think it's very possible, very likely maybe that in a relatively short time period, we've got AI models which can outperform, mathematicians on pretty much everything, right?
At least, yeah, many measurable outcomes. Yeah.
Yeah, yeah. And so I was kind of wondering what you think about, like, in some sense, who's going to pay for that development. So right now, if you prove something that's like Annals level, you get all this hype, right? And all this hype gets venture capital. So like proving theorems directly gets AI companies money, I think, to build more and more. And so we look at this and I say, okay, this looks like it's an exponential growth. And I agree that if the money kept coming in, exponential growth seems very, very possible, maybe likely. But at the same time, once it's the case that you've got an AI company that's producing a couple of annals papers every month, say for instance, right? Isn't the marginal hype going to significantly decline? And then there's kind of a question of, is development going to keep moving in the direction of making pure research math better? When does it make money? Because if it's not hype, it's there's not a lot of money in proving theorems.
Yeah, that's a good question. I mean, I think this depends on like how you imagine the models being trained. If you imagine like a huge amount of money and effort is going into the models, improving the model's ability to do research math, and that's the goal, then I agree that what you're predicting probably comes to pass, like probably eventually they stop improving it. I don't think that's how the models are improving. I think
Mm.
there's two ways the models are improving at math. So one is they're improving in general reasoning ability, and then part of that is doing math. And that's something that there's a very strong incentive to keep doing if you would like the models to be economically valuable. Another way the models improve is that historically, the labs have found that techniques used to improve math capability generalize, and it's a little easier to see them working in math.
Hmm.
So they often try a technique to improve math capability and then try it to improve all other capabilities. And so if that paradigm keeps continuing, they keep working on math. And then finally, the labs just have a lot of mathematicians, and I think they enjoy working on math, and I think that's like another reason that they keep improving. Like, so I definitely I think like if you ask Sam Altman or like the C-suite of these companies, like why are they doing
Mhm.
math? Probably PR plays a big role. I think if you ask the
Yeah.
actual researchers, that's not why they're doing it. And I don't think there's a good reason to expect economic forces to stop them from caring about math. Like I think that's just gonna that's just like part of the paradigm now.
Do we think there'll be any kickback to the math community? Do you think these companies that are, getting all this free PR and getting richer off of solving math problems and working with mathematicians, will they maybe throw some grants our way, throw some funding? Because I mean, part of me feels like we're being used, and like they're getting richer and richer. And, they've sort of discovered this community of people who's just happy to do work for free, because it's fun and they like math. And they're just like the billions keep coming and nothing is coming back to the math community money wise. Have you thought about that?
A little bit, yeah. So OpenAI says that they want to work with mathematicians to figure out the future of the profession. You can decide how to understand that.
Mhm.
Um, I think one thing they are producing is now interesting mathematics, and that's the goal of at least one goal of the math community. So maybe that's giving back a little bit, but no, I mean, I don't think they're going to give us, a cut if that's what you're asking.
Well, I think that towards giving back, um, maybe much more importantly, is a call for the AI companies to give back towards education in general. And as we've discussed, I think mathematics should be a big part of that. I wanted to highlight something Daniel just pointed out that, these companies, they really care about training these models and they, figured out that, oh, if you train them to be good at math, that generalizes. They'll be good at a lot of other things. I think that's not just AI models. I think that's also true for people. So I think you know, yeah, I somehow think in the big picture, while it would be wonderful to see, grant money coming from these AI companies for research math, and I would very much welcome it. I would also, on a much bigger scale, like to see the AI companies uh, commit money and resources towards this goal that we were talking about earlier, keeping an educated humanity. I think
Mm.
that's really the bottom line, big ticket important thing.
Yeah, although they might push AI tools for that education, which might undercut, um, I don't know. I worry about that. I worry about AI getting too involved in education. I feel like the K through 12 experiment of like every kid has a Chromebook has been kind of a disaster, right? And so and
Yeah,
now a lot of school districts are pulling back and like less screen time in school and more like, thinking in pen and paper. I'm a I think that it would be great to see AI support the value of a math education, right? But I'm not sure that they're going to help us, preserve the quality of that education.
well, I want to point out that one of the things that went wrong with this change to Chromebooks and one-to-one devices is
Mhm.
that there was never data that showed that this was a good idea.
Mhm.
It was a fad, it was an excitement, it was a hype. Now, when the AI companies decide how to train their LLMs, they don't do it based on fads and hypes. They do it based on data. They are very rigorous in their analysis of how to spend money to train LLMs. If we were that rigorous in our analysis of how to educate people, we wouldn't be running into these problems. I think that the failure in what we're seeing with the introduction of Chromebooks, and one-to-one devices and screen time in schools wasn't that um, it wasn't somehow just the fault of the Chromebooks. It was the fault that we didn't have any good reason to think that this was a good idea. And now we're starting to see studies and things that show that it's not a good idea. So we need to take that level of seriousness. We certainly do not need to introduce things into education that might be dangerous without good data and good, science of education.
Right. But at the same time, I think, Google is very rigorous in like its development of its own products, right? But the idea that like, oh, this is going to be useful for education, then we sell a lot of Chromebooks to schools. I mean, this is it's a um, it's a money-making move, right? They might not really care about the education itself. It's just so it's like I just imagine an AI company being like, yeah, every kid should have, access to these models and like, these subscriptions, and school districts are suddenly paying money so that all their kids have access to some latest version of GPT, right? And, that'll be a good business model. Anyway, this is
Yeah.
maybe a different conversation,
But
but
that's clearly the opposite of helping education. I
right,
think we can all
exactly,
agree.
exactly. So I worry, so maybe it's better if they just don't get involved in education. That's sort of my sense. Um, this has been, such a great conversation. But Joel and I had thought about like giving you guys both the opportunity for like final thoughts if we're ready for that. Just, take a few minutes and give us your final thoughts on, I guess, on all of this or any of it, or maybe one particular piece you wanted to say something more about.
I mean, maybe I can say, I think we've talked a lot about the dangers to the profession, or like how the profession will have to shift, and like changes to how we educate students. And there's definitely like a lot of dangers and a lot of uncertainty. Like I also think in a lot of ways what's happening is really exciting. Like we have tools that can be used to produce good science. Many of the ways they're being used are not to produce good science. Like a lot of what's being produced is slop or whatever. We talked about that. But I think as capabilities improve, like it's really exciting that we'll be able to use, we'll have powerful tools and do cool math. And like at least for me, like my primary goal as a research mathematician is to like learn and understand cool new math, and produce cool new math. And like I I'm very excited for tools that let me do that. Like I don't think it's not only danger. Like if you value the outputs of the profession, like this is primarily an exciting time.
I'm glad that we had some chance to talk about education, even though this started as a question about research. Because actually, if you think about the business model that supports having academic mathematicians, it is largely dependent on our role in college mathematics education. And I actually think that that's one of the most important tasks we have ahead of us right now is to think about how we preserve high quality mathematics education despite the availability of AI tools, how we continue to help demonstrate that mathematics education and the kind of reasoning skills that it gives people are really valuable and things that we want everyone to have no matter what AI can do. I think those are actually some of the most important things that we need to be thinking about right now as mathematicians.
Excellent. Well, thank you both so much for being here. It was an absolute pleasure to have you here, and I hope we can have you on the show again. Thanks for listening to Academia on the Line. Today's guests were Daniel Litt and Melanie Matchett Wood. Daniel is an assistant professor of mathematics at the University of Toronto, working at the intersection of algebraic geometry, number theory, and topology. After receiving his PhD in 2015 from Stanford, he held positions at the University of Georgia, the Institute for Advanced Study, and Columbia University. He is a Sloan Research Fellow, a Fellow of the American Mathematical Society, a recipient of the Ontario Early Researcher Award, and a recipient of the 2025 Kathleen Morowitz Prize. In the fall, he'll be the Benedict Gross Distinguished Visitor at Harvard University. Melanie Matchett Wood is the William Casper Graustein Professor of Mathematics at Harvard University. She received her Bachelor of Science in Mathematics from Duke University and her PhD in Mathematics from Princeton University. Following an American Institute of Mathematics 5-year fellowship and a Zago assistant professorship at Stanford University, she held faculty appointments at the University of Wisconsin-Madison and the University of California, Berkeley before joining Harvard in 2020. Melanie has received a Sloan Research Fellowship, a Packard Fellowship for Science and Engineering, a Presidential Early Career Award for Scientists and Engineers, the National Science Foundation's Alan T. Waterman Award, and a MacArthur Fellowship. She is a Fellow of the American Mathematical Society, an honorary member of the London Mathematical Society, a member of the American Academy of Arts and Sciences, and a member of the National Academy of Sciences. The theme music is Ophelia's Blues by Jason Shaw from Audionautics.com, and it's used under a Creative Commons Attribution License. Thanks for listening, and we hope to catch you on the line.